As we listen to Radio Dabaga from Vatican to Africa, we're looking at this Mark I receiver that's working pretty good now, but can work better. You'll notice that the lid is off. So it looked good. It was chrome paint with another layer of gloss on top of it. It looked really sharp. And then I put it in here and ran it, and you'll see here in this picture that I inserted that well, this little laptop fan cord sunk right down into that paint like a warm knife into butter, and the feed of the little digital display up here also just sank right down into it, and so that's all been stripped off. And now I have put on engine motor paint, which will not be affected by temperature, and you're limited in your colors. You could have had a bright orange or a really metallic kind of blue. Didn't seem to work well. There was a red, so I just chose white. There's a silver too, but I'm almost scared off of silver. So anyway, so here's an interesting thing to note. The digital display is, when you have it tuned in, when you have it in the normal position, that's actually the upper sideband position. And so you're looking at the upper sideband of a carrier and so you tune to 15,549 and then look at the upper sideband, which is at 1550, if that makes sense to you. And the same way, if you go to lower sideband, then we would tune in the other direction. It's tuned in at 1551. But we'll get into that in just a minute again. Just while we're here, we're looking at this. Alright. So I don't just restore these things and go. I use them for a while. It's called burn-in, really. And this had some burn-in issues. For example, this is still too loose. It's not absolutely solid. When I took that steel dial cord off, it was tight as it could be, almost torqued tight, probably torqued tight, which I will have to work on. So I took this out and there's a mechanism here that holds the pulley. I just rotated it just by the thickness of a washer to tighten it. And it's still a little loose, so I'm going to need to pick a little thicker washer, maybe by 0.5 millimeter. Another issue I found was that it seemed disappointingly sensitive on the first 3 bands. It's really nice on this 4th band. And so I did some tweaking in the RF alignment to improve that. Another issue is that the passband on the, let's turn this down, it's hard to talk over that. The passband on the second IF mixer box is, I like to run these things at the closest I can to instability, in the sense that it will be the most sensitive in that condition. But it was actually, the crystal activity was stopping in a few places, and in overpowering, you know, the foghorn type stations that come in really strong, were causing this crystal activity to stop. And I have been corresponding with Gary, WB6OGD, is a ham radio operator on the Hallicrafters radios group, and we've been talking about the SX-96 and the SX, I believe it's 101 and 117, which are similar designs with this 1650 first IF and 50 kilohertz second IF, and basically the crystal on the lower sideband is at 1600 kilohertz right on, but the upper crystal has drifted up over the years to 1702.333 megahertz. It's actually 1703.2.333 kilohertz, and that's logical because, and here's we'll say a principle. It's on lower sideband right now, but upper sideband is the same thing as normal. There is no difference. There's a treble cut in the middle, but the idea of upper sideband and lower sideband is just to switch back and forth like that, but this is the same thing as upper sideband. And so 99% of the time this radio is in the upper sideband mode. And in fact, 99% of the time or more, people don't use lower sideband, they use upper sideband. All the utilities, all of the aircraft, all of the just everything you find in single sideband mode is upper sideband. Weather channels and marine weather. You go up and down the amateur band, they seem to pretty much have using upper sideband, and that actually creates more separation. If you had somebody on lower sideband and another one on upper sideband, and it would look like you're the same, but you're actually walking on top of each other. So most people by convention have been using upper sideband. So here's the principle, Alvar's principle. Don't know if it's scientific or not. The more you use a crystal, the more it drifts. And the upper sideband crystal has drifted, which gives an opportunity in the alignment of this receiver. In particular, it's really not just align the 50 kilohertz, then align the 1650. It's align the 50 kilohertz, then align the 1650, then go back and look at the actual crystals that you'll see when you do the 1650 and divide it in half, and in fact this thing should be aligned to 51.1 whatever, however the math comes out, on the 4 50 kilohertz IF transformers. And that seems to me a worthwhile thing to have me pull a case off. So let me put this up and show you another view, and we'll go from there. Alright, so we're looking at the underside of the radio, and this is something that's good to know. These, the T9, which is the passband IF on the second IF mixer is, which is a switchable upper and lower sideband. Well, the upper sideband IF's slug. Thank you. Okay, so you can actually access that slug with a tool like this one, just from this hole, and it goes all the way inside that mixer box, and with a little careful and delicate touch you can insert this into that slug screw slot. Okay, I'm not going to take the time to do that, but it takes a little time, a very delicate touch. You can get it all the way in there, and that's what I did to adjust the upper sideband so that no signals would overdrive it and cause it to stop oscillation. Okay, so since we'll be taking the case off and re-accessing these, actually I need to hook up the spectrum analyzer again and the signal generator inside. That's why I have to take the case off. If it was just adjustments, you could do it all from the top side, but you need to actually do that. And then while we're at it, another little interesting pet peeve of mine is these holes. Well, I don't know, maybe they bought a whole bunch of these cases one time and then bought the trimmer, but the trimmer doesn't line up with that hole. Now, at least I suppose you could adjust it here or there or something like that, but when it fits in all the way around, you miss, okay? So you've got that one, plus I've had to relocate one right here. So I will take the opportunity, without knocking the camera over, to drill out these holes a little bit so that you can access the trimmers more easily. Right there, and so forth. And so we'll, there'll be this one, this one, this one. Look where that one is. By the way, it's backed out all the way for 14, which means that you will actually hit that thing and crack it more. The coil form is already cracked, but it's so soldered in, it's no big deal, and it doesn't affect the inductances or anything like that. So step one is always to insert that in farther, then come back, and you'll have to realign it when you put the case back on. So that's what is also on the hit list, so to be, the punch list for when the case is removed. Okay, 8 man-hours later at least, I've got it where it needs to be, and it took some reconfiguration. I took the speaker out because a sweet noise was nauseating and put in a 4-ohm dummy load, and it turns out that well, let me just say that the spectrum analyzer is picking up again off of test point A on the schematic. This signal generator is sweeping from 1400 to I don't know, 1800 or something. And at, I believe, at 1000 hertz. and it's a pretty stable picture there. You're looking at the upper sideband. You may not be able to see it, but this peak right here, let's knock all the wires so you can. Okay, this peak is the 1700 kilohertz crystal. This is the passband right here at 1650. And then on the lower sideband, I think we're pretty much at the same level. Yeah, very close, right? Which is also a desirable point to be. That's the lower sideband crystal at 1600 kilohertz. It's no drift at all. So this is this allowed. What I did was I basically set it up to do both IFs at the same time. So this is picking off at test point A. The signal generator is putting in a sweep at from 1400 to whatever, 1800 or something, and at 1000 hertz. And then this is, instead of the speaker, there's a dummy load, and this is reading volts, AC volts, at the speaker terminal, and which is also in the spec for looking at the 50 kilohertz. So I adjusted the 1650 IFs to get right here. Took a lot of time finding the right place, and then adjusted this for the maximum output on the 450 kilohertz IFs. Now it says 50.5, but they're actually, I think, at 50. We'll see. We still got to see how the BFO will work in the upper and lower sideband and stuff like that. And we do a reasonableness check as well. Is it deaf, or is it actually picking up signals? If it's deaf, then I'm all wet. I will go in and capture the 50 kilohertz just to see what the curve looks like. So I have to reset up all this to do that, which the input for the signal generator is at test point A, and the output for the spectrum analyzer is the insulation on the test point B. Okay, what we're looking at now is just the second IF at 50.5. I've actually tuned the second IF to 50.5 per the specs rather than 50.0, and the oscillator tube for the first IF is taken out, as it says in the instructions. And so you see the curve. It's not sweeping. When you sweep, it just makes a plateau. It's basically doesn't help much. So I'm just doing the peaking of those IF cans to 50.5 as indicated with the maximum on the output to the speakers. So now what remains is to take all this stuff off and see if the radio works or not. Okay, so I've got the antenna hooked up to it. It's about noon time, and so it's terrible conditions. This is CFRX in Toronto, and this radio is finished with its alignment. It's working very, very well. So we'll take a break now and come back and address the other punch list items. Okay, so what I've been doing here is I've been determining the minimum detectable signal. And to do that, you need a signal generator. It's over here. And calibrated attenuators, and in this case I can't do it the way I've normally been able to do it, because this is a got both an upper sideband and a lower sideband mixer for the second IF, and that creates quite a bit of complication. First of all, when you determine the minimum detectable signal, let me do this so that I can see what I'm doing here. So when you're doing a minimum detectable signal, the first thing you have to determine is the correction factor, which is just a formula based on 10 log 10 times the bandwidth in hertz. And the point behind that is that you add that correction factor to the basically the noise of a perfect resistor, which is minus 174 dB, and so the outcome of the correction factor, so any radio is never going to be able to beat this, is a minus 147 dB. M. Actually, it should be M, but anyway. So the typical solid state, really high quality solid state transceivers, radios, this Japan radio is going to have something in the range of minus 130, 135 or something like that. Really good minimum discernible, the word is discernible signal, not detectable. I keep saying that. I even wrote it down. So you have a lower sideband and an upper sideband. And the problem is there is a beat frequency associated with the lower sideband oscillation. And there's also one associated with the upper sideband. So when you're measuring, you're going to have two beat frequencies. You're going to have the one from the sideband response as well as the modulation from the carrier. And the modulation from the carrier is what you're actually measuring as the minimum discernible signal, because basically you have it in single sideband, you're say on an amateur band or something like that, and you're trying to pick out somebody's Morse code or something like that, and the most faintest signal is what you're looking for in this measurement. So the voltmeter just gets confused, and I get confused, and I could switch back and forth, which is what I was doing for a while. It just got to the point where things would move out before you'd have a chance to go from one to the other. So I used my ear. And if you've ever had a hearing test, you know how they can get really faint. And so the ear is not a bad instrument for measuring minimum discernible signal. It's just not quantitative, it's qualitative. But still, I got to the point, what I would do is I would use the calibrated attenuators until where a 3 dB difference in the attenuation was the difference between I could just barely hear, and it didn't make any difference whether and with the 3 dB additional in the circuit, I couldn't tell whether the signal generator was on or off, or output or no output. So if I couldn't tell, that's, we're beyond the limit of being able to discern something. But if you remove 3 dB from the attenuation, and I could tell, then that was my indicator. So I got a good result in the first band in the range of 1 microvolt. That's pretty good. I think it could probably be better, and maybe with a lot more thinking and tweaking and so forth. Part of the problem is we had to substitute one of the trimmer capacitors, and that may have had some effect. On the second band, it was in the range of 0.4 to 0.8, which is pretty close, less than 1 microvolt on band 2. And then bands 3 and 4 on the range of 0.1 microvolt, which is really, really sensitive. And has been proven out in the burn-in. Sorry, my battery ran down. What I was going to say on the image frequencies is that wherever you would find an image frequency, I found none, and my injection signal was 70 dB over S9, which was huge. Over, it's like 200,000 microvolts or whatever it is. Yeah, it's a 0.2 millivolts or something like that as an input signal, and which is a really big signal, and still there was no image frequency. So after trying that for 3 different frequencies, I gave up. Now the problem is it's probably got one, and it may even have them at the 50 kilohertz level, but what you get into is that your signal generator starts generating image frequencies when you get so high, and the radio actually picks those up. So I only have S-meter measurements to take, and I think I'm going to probably wait to do that and call this video complete. Well, tonight I'll tune in a couple stations for you to give you an idea of just how powerful this radio is. So we'll continue with that then. So I had to throw away the tape from last night of Radio Sudan and All India Radio, Vishwavani is what it's called in Hindi, because I forgot to turn on the sound, but the sound's on now. So you're listening to Radio Nacional Amazonia from Brasilia. This is mid-afternoon, about 2:30, and a very excellent signal reception on the SX-100, and we'll tune that a little better, and very comparable, in fact indistinguishable from the signal from the Japan radio JRC 535D. Very good performing radio. I did run through the I put in an input signals to the receiver from the signal generator that were calibrated in terms of volts and dB, and what I found is that all in all the S meter is very close to S9 is very close to the standard of minus 73 dB or 50 microvolts at the input, with the exception of band 2, which is it's a little bit springy on that one. But for the other bands, there's nothing. There is a quote calibration procedure in the service manual, which has you backing down or the sensitivity to make it agree with the actual input, but there'll be none of that here as I run everything flat out. So this completes this radio. It's in an excellent runner, and it'll probably be my primary shortwave listening radio along with the Japan radio. And so this is Hallicrafters Rehabs. Thanks for watching. Thanks for the new subscribers.